Christian Gertig. I've been working in the solar energy industry for the last 12 years. Today I'm going to tell you about the photovoltaic system design for rural electrification applications. The course outline will cover at the beginning aspects of the solar resource to understand where the solar energy comes from, the dimensions, parameters, etc. Then we're gonna follow up with basic photovoltaic system componentry, the major components and selection criteria, photovoltaic system design in order to be able to size these systems, and in the end, various online tools and resources that will help you along the way in order to size systems adequately. The solar energy hitting on solar panel surfaces to produce electricity consists of various components. The overall solar energy collected by a solar module is called the global irradiance. This means it is all the fractions of the solar energy that occur, which are the direct radiation, which is directed sun rays coming directly from the sun. These only occur if you're actually able to see the sun. So when you're looking at the sun and see the sun's disk, then you have direct radiation. If the sky is clouded, you will not have direct radiation. Radiation scattered through clouds is called diffuse radiation. This is still capable of producing electricity in non-concentrating systems. So normal solar panels will be able to produce electricity of diffuse radiation only. You can say roughly 20% or so of the energy of the solar panel rating can still be produced with diffuse radiation. And then you can also have reflected radiation from the ground produce electricity. This may be taken into account when designing the system surroundings. The unit of measurement is watts per square meter of the solar radiation, and the panel rating is measured in watts. Instantaneous values of solar power are measured in watts per square meter and are called solar irradiance. Energy values for solar are called solar irradiation and are measured in kilowatt hours per square meter. Solar panels are rated at 1000 watts per square meter of solar irradiance. As you see on the right, a typical daily profile of solar irradiance during the day rises from 0 in the morning towards 200, 500 and over 1000 during the midday in good summer days, and sets again at 0 watts per square meter. If you integrate the solar energy during this period under this curve and normalize it to 1000 watts per square meter, you get the total number of peak sun hours. This is an indicative value for the solar resource existing on a certain site. The higher this value, the more your solar panels will produce for a given site. The solar power or solar irradiance outside of our atmosphere, the extraterrestrial solar irradiance, is called the solar constant and is fairly constant. Nevertheless, due to the different angle of incidence on the Earth's surface, this solar irradiance is being reduced by a certain amount. The more atmosphere the sun has to surpass, the less irradiance is actually hitting the ground. You can see this on the right. During early morning or evening sunrise or sunset, the sun has to pass through more air mass, and therefore the solar radiance is reduced as it hits the ground. In summer, midday, as you see on the bottom, the sun has a steeper angle, and therefore more irradiance is reaching the ground and therefore your panels will produce more electricity. As we just learned, the solar constant is the maximum value of solar irradiance that can be measured outside of the Earth's atmosphere. It is 1367 watts per square meter. After passing through the atmosphere and hitting the Earth's surface, high values measurable on Earth can amount to 1100 watts per square meter. PV modules, as mentioned, are rated at STC, standard test conditions, at 1000 watts per square meter and a air mass spectrum of 1.5 and a ambient temperature of 25 degrees. Approximately half of the global solar resource occurs below 800 watts per square meter. This is due to reduction factors that occur for aerosols in the atmosphere, as from moisture, dust, or pollution. There are certain angles relevant in the solar industry. First of all, the latitude is very important. It can tell you a lot, especially the solar resource that you can expect. The higher the latitude value in positive or negative, meaning the further away from the equator you get, the lower solar resource you can expect. Another angle that is very important and you come across a lot is the solar elevation. This is the angle measured from the horizon line to perpendicularly above you. It is from 0 to 90 degrees above. Another angle is the solar azimuth, which is the angle measured from east to west. It is basically the angle the sun surpasses from the morning, rising in the east, to the evening, where the sun sets in the west. The rotation axis of the Earth is tilted by 23.5 degrees. As the Earth travels around the sun, due to this effect, you will have longer and shorter days throughout the year. This has an impact on the available solar resource, as in winter the days are very short and the solar elevation, the angle from horizon to the maximum during midday, is lowest. In summer, the days are much longer and the solar elevation reaches its highest point. Summer solstice is the point in time where the sun is at its highest point. This occurs in the northern hemisphere on 21st of June, whereas winter solstice is the point where the sun is at its lowest and the days are shortest in the northern hemisphere on the 21st of December. The times in between 21st of March and 21st of September are called equinox. Here you see an example of a solar resource map of the Earth. It shows in darker red colors the regions on Earth where most solar resources available and solar systems will perform optimally. As you see, it is around the sun belt, as it is called. It is roughly the equator plus minus 30 degrees of latitude. This is the region where most solar radiation occurs. There are regional differences due to the altitude. As you can see, in Chile, it is a very high mountainous region. Australia is also very good, and North and South Africa, as well as the Middle Eastern region, and Mexico and California. This slide shows a close-up on Africa for the same solar resource map. Here you see the best regions in the African region and the Arabian Peninsula. As you see in the northeast, and in Namibia in the southwest, the values are highest. They are measured in kilowatt hours per square meter and year, and as you see, values of up to 2500 kilowatt hours per square meter can be achieved. Solar panels consist of solar cells, which are semiconductors commonly produced from crystalline silicon. As soon as sunlight or photons hit the surface of the solar cells, electrons are created, and due to the internal electric field of the semiconductor, these electrons can be channeled to the busbars, which are the electrodes attached to the solar cells, and then an electric current can be created and channeled to electric loads to provide, for example, lighting. Solar panels are measured in watts. This is the maximum power a solar module can produce under 1000 watts per square meters. Most of the solar modules consist of polycrystalline silicon PV cells. You see that on the left, they have the typical pattern of cells being connected in series with bypass diodes inside to alleviate effects like shading. However, other technologies also entered the market. For example, thin film PV modules, which consist mainly of a cover glass where it has a semiconductor sputtered on it. These are a bit lighter and a bit cheaper, but also less efficient. Furthermore, there are amorphous PV modules. These can be shaped in any way and attached to flexible surfaces. Nevertheless, the efficiency is quite low and the utilization is still very low.
The charge controller is a device that's used to regulate the electric current entering and leaving the battery. It comes in two types, pulse width modulation and maximum power point tracking. Pulse width modulation uses constant current to charge the battery, whilst maximum power point tracking uses the voltage corresponding to the maximum power of the PV at any given time to charge the battery. Though pulse width modulation controllers are cheaper, maximum power point tracking controllers can save considerable money on systems, as they provide up to 30% more power to the battery for a given PV array size. Charge controllers should be matched to the electrochemistry of the battery. They should be sized such that they can accept the maximum current and the maximum voltage of the PV array, and also output the voltage of the battery. The battery bank is used to store excess electrical power generated by the PV array. Batteries use an electrochemical reaction to generate direct current to power direct current devices. Batteries come in different electrochemistries, though the most widely used is probably the lead-acid battery. Battery chemistry should be selected depending on the load requirement and the operating environment. Batteries are sized based on the power requirements of the electrical devices they supply and the number of hours of non-daylight operation. Many devices, such as electric motors and compressors in refrigerators, have surge currents on startup. Battery banks should be sized correctly to account for these surge currents. Battery performance and life cycle are dependent on operational factors. The depth of discharge of a battery is a measure of the percentage of its capacity that has been used up. For instance, lead-acid batteries are typically discharged to 50% of their total capacity. The daily charge-discharge cycle of the battery can also be a factor in its performance. Lead-acid batteries, for instance, have a reduction in their capacity if left partially charged for extended periods of time, and therefore need to be regularly topped up. An inverter is a device that converts direct current into alternating current. This can then be used to power electrical devices that run on alternating current. Depending on whether or not alternating current devices are being used, an inverter can be completely done away with in an off-grid solar PV system. Inverters should be sized to accommodate the maximum voltage and current from a PV array. This slide gives a list of elements to be considered in designing a PV system and matching its components. Further considerations include intended lifetime of the system, degradation of its components over that lifetime, and the operational environment. With a view towards lifetime performance, high-quality system components should be sourced as much as possible. Although they require a higher upfront cost, they represent higher value for money because they last much longer than cheaper alternatives. This slide contains a table of commonly used appliances and their power requirements. This provides useful information for sizing a PV system. This slide contains the procedure for sizing the components of a solar PV system. This involves, first of all, determining what services are to be provided for by the PV system. This gives us an understanding of the daily energy requirements. Once this is known, the battery bank, PV array, and other components can be sized based on the previously mentioned design considerations. This slide gives a possible layout for an off-grid PV solar system. It would provide power only for DC loads. This is a possible configuration for a system that caters to both alternating current and direct current loads. This is a possible layout for an application-specific system, like for instance a solar PV system powering a positive displacement water pump. The water pump in this layout is assumed to be a direct current device. Systems that are designed to operate only on direct current should be done so keeping cable length and current magnitude in mind. With DC systems, high current and long cable runs lead to high resistive power losses. Therefore, components should be placed as close to each other as possible to minimize cable runs. Also, a high voltage battery and pump should be selected in order to minimize current magnitudes. Based on the water requirements of the application, a simpler version of this system would do away with both the charge controller and the battery bank, leaving the pump to be operated by the PV system directly when there is sufficient sunlight. The following few slides provide an example of the process of designing an off-grid PV system. The application is to provide electricity for both alternating current and direct current loads at a village community center. The daily energy requirements are calculated, with refrigeration and air conditioning being the largest loads. The battery bank is then sized based on the daily load requirements. A lead-acid chemistry has been selected in this case because it is widely available and has good surge current capabilities. Battery technical data should be consulted in order to account for the effect of operating temperature and depth of discharge on battery capacity. Furthermore, electrical losses and conversion efficiencies of the various components should be accounted for. Finally, an energy autonomy period should be selected. This will provide for energy during extended periods without sunshine. Next, the PV array is sized. In order to do this, the local solar resource is determined, as well as the site-specific positioning of the array. Next, electrical losses upstream of the battery and wiring, as well as the efficiency of the battery itself, are taken into account. The sizing of the major components of the off-grid PV system has now been accomplished. The charge controller and the inverter are now sized as required to meet the current and voltage specifications of the PV array and battery bank. This slide gives estimates of the maximum cable length to be used for various current magnitudes and cable thicknesses.
A set of very useful online tools is provided by SolarGIS. The tool iMaps is used for early prospecting stages for projects. If you're looking for site selection for solar projects, here you can see various layers on a Google Maps surface. You can zoom in to specific countries, latitudes and longitudes, and see the solar resource that exists on site, the ambient temperature, the population, the terrain, the usage of the terrain, and major infrastructure around. This is very useful to select sites on an early stage. The other tool, the PV Planner, is used to estimate the production of photovoltaic systems of certain configurations for the given site, and can be a preliminary indicator to do rough pre-feasibility studies. Another very useful tool is PVGIS. It is online and can be accessed for free. It allows the estimation of the solar energy production of a PV system for a given site, which can be selected around Europe and Africa. It allows output of expected production as well as radiation values, and even allows the design and production estimates for standalone photovoltaic systems.